All right, so we have propane gas at 298, 1 atm, coming in with 150% theoretical air. Also coming in at 298, and then everything exiting at 600 degrees or 600 Kelvin. And we want to find a couple of things. We want to find the mass flow rate of the fuel. So we want to find m dot f. We want to find the balanced chemical equation. Okay, that is what it is. We want to find the mole flow rate of the entering air. So we want to find N dot of our air. We want to find the dew point temperature of the water and the products. And we want to find the rate of heat transfer, Q dot in kilowatts. So, oh, and we are also given that fuel, I didn't write that down, but our fuel is coming in 1 kilomole per second. All right, so I'm gonna start throwing my solution over here. As far as your assumptions go, not too much. Steady state, changes in kinetic, changes in potential energy are negligible. We're also going to say W dot's equal to 0, and we'll be done there. So, okay, so let's see. So first thing I need to do is figure out the mass flow rate. And for this guy, since I know the molar flow rate of the fuel and I need to know the mass flow rate, magic number to go between mass and moles is your molar mass. So I know, right, molar mass is going to be in terms of kilogram per kilomole. So it's mass over moles. And of course, I could put this in terms of flow rates if I wanted to. So that means that the molar flow rate of my fuel would be m dot over the molar mass. So m dot of my fuel. Oh, I'm sorry, I'm not solving for the not solving for the molar flow rate. I already have that. I need the mass flow rate. So my n dot of the fuel is going to be the molar mass of my fuel times the molar flow rate of my fuel. And molar mass, you can look it up for C3H8, or you could do sort of a quick calculation. But it's 44.09 kilograms per kilomole times the mole flow rate, which is 1 kilomole per second. So just ends up being 44.09 kilograms per second. All right, so there's A. Next thing we need is our balanced equation, so no problem. First thing we need to do is we need to find the theoretical amount of air, which means that we need to balance that chemical equation with just 100% theoretical air. All right, so we're going to get some amount of CO2, some amount of H2O, some amount of nitrogen. So you could see that, well, I have 3 carbon on the left-hand side. I got 3 carbon on the right-hand side. I have 8 hydrogen on the left-hand side. I got 4 times 2 hydrogen on the right-hand side. So all I've done is I've done a mole balance on the carbon. Then I did the hydrogen. Now I'm going to do it on the oxygen. I'm going to kind of keep my notes down here that I have on the left-hand side. I've got 2 times ATH. That's how many oxygen that I have. And on the right-hand side, I've got 2 times 3 plus 4. So looks like my theoretical air is 5. Yeah. So now I'm done with that. So now I'm ready to get my balanced equation. Okay. Don't need an accent there. Whoa. All right, so C3H8 plus, I have, my theoretical air is 5, but I'm multiplying it by 1.5, so it would be 7.5. So 7.5 times O2 plus 3.76 nitrogen can give me some amount of CO2, some amount of water, some amount of nitrogen, and then because we have excess oxygen, if I want everything to balance, I got to have some oxygen over there. All right, so again, I'm doing a mole balance on each one of those elements. I'm going to start with carbon. On the left-hand side, I've got 3. That means there has to be a 3 right here. On the left-hand side, I've got 8 hydrogen, so I have to have 4 times 2 on the right-hand side. And now I'm going to do mole balance on the other stuff. So for my oxygen, on the left-hand side, I've got 2 times 7.5. On the right-hand side, I've got 2 times 3 plus 4 plus 2 times whatever goes in that blank, right? So I could see that, all right, so I got 15. So let's see, it had 15 minus 10 divided by 2, yeah. And that would be what goes in that blank. So 2.5. Okay, so 2.5 goes right there. And then for my nitrogen, let's see. So on the left-hand side, I've got 7.5 times 3.76 times 2. And then I've got 2 times whatever goes in that blank right there. So you can see that's just going to be 7.5 times 3.76. What is that? That's going to be 28.02. So 28.2. This guy is 28.2, and so that's my balanced equation. All right, what's the next thing that we need? We need the dew point temperature of the water in the products. So I am looking at these. These are my products. So I know that that's related to, I know the dew point temperature is the saturation temperature at the partial pressure. So TDP, TSAT, at PV, which means I need to find the PV. So in the products, the vapor pressure, if I say that those products are, this is an ideal gas mixture, right? Everything's coming out hot, 600 degrees Kelvin, or 600 Kelvin. So I know that PV over P, remember from unit 4 when we talked about ideal gas mixtures, I know that's related to my mole fraction. And my mole fraction is the mole fraction of the water in the products, right? All the stuff on this side. So I have the number of moles of water, which is 4, over the number of moles of all of the components in that mixture. 3 plus 4 plus 28.2 plus 2.5. And I know the pressure of everything is 1 atm or 101 point, actually, I'm sorry, I'm putting in kilopascals, aren't I? So 1 atm is 101.1325 bar times this 4 over 3 plus 4 plus 28.2 plus 2.5. All right. And so we end up getting, I don't know, what are we going to get? Oh, I think I was supposed to find something else. Maybe this is part D. I'm solving it out of order, but that's okay. But let's see. So I've got a partial pressure of 0.107507 bar. And so all I need to do is I need to look in table A2, or you could look in table A3. It doesn't really matter. Same information contained both places. We're just trying to get what is the saturation temperature at this PV. So 0.1 and change. Let's see. Doesn't really matter. So let's see, 0.107. I looked in A2. So 0.107 would be between that guy. So 45 degrees Celsius and 50 degrees Celsius. So it's as closer to 45 than it is to 50. But yeah, so you can interpolate. Actually, it looks like it's right in between, isn't it? 0.107. Yeah, what did I? 47. Yeah, I'm guessing that I probably did it in here. So got 45, 47. This would be our TDP. And you'd interpolate, like this is your vapor pressure, this is the corresponding saturation temperature, 0.09593, 0.1235, and then our vapor pressure, which we just calculated, is going to be the 0.107507. So hopefully we've got something that looks like about 47.1 degrees Celsius. All right, so that would be the answer for part D. But of course, we need part C. We'll click on that. So part C is asking for the molar flow rate of the air, of the entering air. So I need the mole flow rate. Nope, not the mass flow rate. I need the molar flow rate of the air. Okay, so for this, I do need my balanced equation. So I'm actually going to copy it again. So I've got C3H8 plus 7.5 times my oxygen plus 3.76 nitrogen, and that's going to give us 3 CO2, 4 H2O, 28.2 nitrogen, and 2.5 oxygen. All right. And I know that the molar flow rate of my fuel is 1 kilomole per second. And so what I need to do is I need to relate those mole flow rates. Well, I have the ratio of the number of moles of air to the number of moles of fuel. That guy. And so what I'm going to do is I'm going to say, well, that's the same ratio, right? This would be on the for the air, it would be 7.5 times the number of moles in the parentheses, which is 4.76. And then for the fuel, it's just 1, right? So it's the coefficient in front of whatever that term is, right? Which is just a 1. All right. But I also know that this is, well, be the same for the molar flow rates, right? So yeah, from there I can get that molar flow rate of my air is going to be 1 kilomole per second N dot F times that, right, N dot F times 7.5 times 4.76. So 1 kilomole per second times all that. Let's see, so yeah, 37.5. So 37.5, I'm sorry, 35.7, apologies. And that's going to be kilomole per second. There we go. So that's D and C and D, and now we need E. All right, so again, I'm going to need this guy, C3H8 plus 7.5 times O2 plus 3.76 nitrogen gives us 3 CO2 plus 4 H2O plus 28.2 nitrogen plus 2.5 oxygen. Let's go ahead and there we go. So I need to apply my conservation of energy. All right, no problem. So I know that I have an equation for Q dot over N dot of my fuel. Keep in mind that the N dot of my fuel is just 1 kilomole per second. So the fact that I just want Q dot is going to be really easy because if I multiply this by N dot F, right, this is 1 kilomole per second, right, that's going to give me my Q dot. So I'll just kind of put that, this is my spot for all that. Q dot over N dot F, my first law tells me that this is going to be the sum of the number of moles of product times enthalpy of formation plus the enthalpy at whatever temperature that those products are coming out at. Well, everything is coming out, all of this stuff. Oh, all this stuff is coming out at 600 Kelvin. And then luckily all of our reactants are coming in at 298 Kelvin, which makes things super nice. So I've got enthalpy of formation plus the enthalpy at the temperature that they're coming out at, 600 Kelvin, minus the enthalpy at standard reference state. Okay, minus number of moles of reactant times enthalpy of formation plus enthalpy at standard or at the temperature that those reactants are coming in at, which is 298, minus the enthalpy at standard reference state, which is also 298. Super convenient, so those guys go away. All right, so now I got to plug in some numbers. So for the products, I'm going to have 1, 2, 3, 4 terms. So I'm going to have 3 kilomoles of CO2 per kilomole of fuel. So it's going to be 3 times the enthalpy of formation for, let's make this, for each of these terms. This can be found in A25. This guy can be found in A23, as can this guy. And that one is A25. So I won't, I'll kind of, let's not flip back and forth, but enthalpy of formation for CO2 from A25, make sure you see it, is negative 393,520. Enthalpy at 600 Kelvin, I'll go ahead. I'll mainly go ahead. Let's see. Close. So it's just annoying enough to be on the other side, but it's fine. Here we are, 298. I'll at least highlight those so you can see the numbers we're going to be pulling off. So, oh, and by the way, enthalpy of formation for some of these guys can also be found here. Yeah. So for CO2, there's that guy. For water vapor or at standard reference state, we'll also need this guy at standard reference state and this guy at standard reference state. So those are all going to be the ones at 298, and then you can scroll down to get the ones at 600. And I realize my face is probably in the way. So there's that. There's that. There's that. There's that. All right, so that's where the numbers are going. As far as what number, where they're going, well, we'll write them down, make sure we got it. So at 600 Kelvin for CO2, I've got 22,280 minus at standard reference state 9364, and the units here are going to be kilojoules per kilomole. All right, and it's kilojoules per kilomole of fuel because this guy is kilojoules per kilomole. I'm sorry. This guy is kilomole of CO2 per kilomole of fuel, C3H8. And this, all this stuff on the inside is kilojoules per kilomole of CO2. So what we're ending up with is we're going to end up with kilojoules per kilomole of C3H8. Yeah. I'm going to kind of clean that up a little bit, but just be aware that that's why the units work out the way that they do. All right, so that's CO2, and then we've got water. That's the next product. So I got a 4. For water vapor, our enthalpy of formation is negative 241,820 plus the enthalpy at 600 Kelvin, 20,402 minus at standard reference state 9904. Same units plus. Now we got our nitrogen. So enthalpy of 28.2. So our enthalpy of formation for nitrogen is 0. Enthalpy at 600 is 17,563. And at standard reference state, we've got 8669, same units, carrying all the way down. Plus, now we got our oxygen. So I got a 2.5. And then the enthalpy of formation for oxygen is 0. And see, at 14, I'm sorry, at 600 Kelvin, I've got an enthalpy of formation, or enthalpy H bar of, I'm sorry, I think I missed 563, yeah, 17,929, and at standard reference state 298.8682. So that's for oxygen. And then of course, now we're at the reactants. But if you'll notice for the reactants, we're only going to have enthalpy of formation because the other two terms just happen to cancel out. So I have 1 kilomole of fuel per kilomole of fuel. And our enthalpy of formation, which you can look up that enthalpy for formation of C3H8 in table A25. So this is gas. I think there's might be something different. I think there's there should be one for liquid as well. But you can go back and look at 825. Actually, we're close enough. Let's do that. Just to oh, looks like they only give us gas, but just be aware that sometimes you get a fuel and it like octane, for example. Yeah, there's enthalpy of formation is going to be exactly the same. Oh my goodness, for liquid and gas, but it comes into play with like water. Oh wait, I'm like, why is that the same? That doesn't make any sense. There's our enthalpy of formation. That's the molar mass that I just circled. It's been a long day, man. All right, so just be aware, pay attention to the phase that it's in, because the enthalpy of formation will be different. In this case, okay, great. I've got negative 103,850, same units, or there we go. And then you really don't have to write anything else, because for the reactants, that enthalpy of formation for oxygen and nitrogen is 0. So it's not really going to matter anyway. I know I wrote some numbers for oxygen and nitrogen, but you notice on the solution, but you notice they just cancel out anyway. So it doesn't really matter. But I've got Q dot over N dot F is equal to negative 1.69, and it's kilojoules per kilomole of your fuel, which is C3H8. And then if you plug that in here, the number is not going to change, but the units will. It'll be kilojoules per second. Yeah. All right. Is that it? I feel like maybe there was something else. Yeah, that was it. All right. Well, let me know if you have any questions. Thanks for watching.